This is a vision transformer I trained from scratch, detecting different types of candlesticks in real time. I wanted to see if I could train a deep learning model to detect 5 different patterns. The game plan was to grab a screen grab of a trading chart, chop it up into image patches, and then bang it into a vision transformer. I'm going to show you how to do it from scratch in 60 minutes. But do you need a GPU to train it, and how fast does it run on a MacBook? And couldn't I just do this with multimodal LLMs? I collected over 2,000 labeled images, hand labeled a ton of them, and trained the model from scratch to help speed up the learning for you. And I found a couple of training twists along the way that helped get it across the line. I'm gonna break it down into 4 simple stages. The first is to get it up and detecting on your machine in 5 minutes. Alrighty guys, so we are going to be building our very own vision transformer to detect different types of candlesticks. Now, what I want you to do before we actually go and start training the model, taking a look at the data, all of that good stuff, is I want to get this up and running on your machine. So I've tried to make this as easy as possible. I've uploaded all of the code onto GitHub, and I've actually uploaded my final set of checkpoints. So you can see over here, it's called 25_model. All the data, everything that you need to get up and running is available in here, and I'm going to be making updates to this, ideally to make sure that we have no dependency issues and that you can run this on your machine. So what I want to do is set a little bit of a challenge. So I want to see if we can try to get this up and running within 5 minutes. So I'm going to start completely from scratch on my machine. So I'm going to go 5-minute timer. Keep in mind, I'm running this on my MacBook, so no GPUs here. So you should be able to get it up and running on yours without a GPU. Okay, so what we're going to do is we're going to grab this GitHub repository. So it's github.com/nicknocknack/VIT candlesticks. I'm going to copy this. And I'm going to jump back into my favorite code terminal, which is going to be, or favorite IDE, which is going to be VS Code. And I'm going to type in git clone and then paste that repository there. So this should clone down the repository. So all the code, all the data, all the checkpoints. There is one trick with the checkpoints in that I've uploaded it using Git large file storage. So it is a larger file. It's around about 100 megs. If you see that it's not 100 megs when you go and clone it, I'm just going to show you how to do that in a second once we've downloaded it. All right, cool. That's everything downloaded. In a sec, we should get our checkpoints. Boom. Okay, there we've got it. So just a good thing to check is if you jump into the folder, the size of the checkpoints should be 102.3 megabytes or around about that size. So it should be 100 megs. If you're getting a much smaller file, what you need to do is you need to make sure that you clone it using Git large file storage. So I'm just going to clear this and we're going to jump into that folder. So cd vit candlesticks. And then what we want to do is we just want to run git lfs pull. So that will just make sure that we've got the checkpoints. You can see I've already got it downloaded, so I don't have the pointer anymore. Okay, so that should be our model now up and running. Okay, there's a bunch of stuff that we need to do in order to get this detecting on our machine. The first and foremost is that inside of this source folder, I've got this file called candlesticks.py here. This actually goes and runs a live Plotly dashboard for live stock tickers using Amazon or using Yahoo Finance. If you want, you can actually go and change the stock code that we pull back. So right now I'm running Amazon. If I wanted Apple, I could just type in Apple here and it'll make detections on Apple, so on and so forth. I've actually trained it across a bunch of different stocks, so should be okay. But for now, what we're going to do is run this. We are, however, going to, or we can change the interval. It looks like I already changed it. If you want them to come a little bit slower so you can interpret the candles, you can change this interval here. I'm just going to leave it as 1 for now. So to run this, let's get our dashboard up and running first. So we can go and run uv run source utils. Let's make sure my head's not blocking it. Candlesticks.py. Now this is also going to download and install all the dependencies you need in your machine. So this is available via this terminal file here, and it should have all of the different libraries that you're going to need. They're all listed out. I'm trying to make this as easy as possible so that it runs on your machine. Okay, so if I go and run this, it's going to create a virtual environment. It's going to install everything that you need. I'm just going to pause the timer while that's installing. We've got 2 minutes left. Okay, so you can see that it says installed 103 packages in 1.85 seconds, and Dash is running on HTTP 127.0.0 port 8050. And you can see that we're serving the flask app. So this means that we are live and running. Now, if I actually go and click this link here, so if you, on my MacBook, I just hit option and then click, take a look. So we've now got a Plotly dashboard with a bunch of different candlesticks. How good is that? Okay. Kind of, yeah, all right. What we do want to do though is make detections on it. And so this is where the live candlestick detection is going to come in. Now, the thing is that I need to have 2 screens to run it. So one where OpenCV can pull the candles, and then a second screen where I can visualize it. So I might have to get I've got a camera here. Maybe I'll just record it on this screen, but it's going to be running on 2 different screens. Okay. So what we're going to do is we've got our candlestick dashboard running. We now need to start the prediction. So I'm just going to split my terminal by hitting this button over here, and I'm going to swap these the other way around. And what I'm going to do is we've got our candlestick still running in this terminal. We want our predictions to run in that terminal. So our predictions are available via this file over here called candlestick predictions. Again, a ton of code's gone into it, and it's going to be able to predict one of 5 different candles. So we've got doji, bullish engulfing, bearish engulfing, morning star, and evening star. So let's quickly take a look at those. So if I go doji candlestick, that's kind of what it looks like. Bullish engulfing, it should be engulfing. That's what you're expecting. Bearish engulfing, so green candlestick encapsulating the red. Sort of the opposite of bullish engulfing, red candlestick encapsulating the green. We then got morning star. Come on, Nick. So that's kind of what you're expecting. So red, so a long red, short green, then long green, and then it sort of goes up. And then evening star, again, is the opposite of that. Evening star candlestick pattern. Cool. So you can see it's the opposite. All right, cool. All right, let's actually start the timer again. Let's go kick this thing off. Okay, so the goal now is to get this up and running. So to do that, we just need to run candlestick prediction simultaneously with our candles now sort of populating. So to do that, we can go run UV run candlestick prediction.py. Now this is going to load up our checkpoints over here. So you can see 25_model.pt. It's going to load up those and it's going to make predictions based on my screen. This is running on a 4K screen, so we might need to adjust dimensions if you're running on a lower res. Let me know if you need that. So if I go and hit that, we should see predictions appearing in orange. I'm just going to get my camera out so maybe we can record. We might need to record. How's that time up? 1 minute 33. Come on. All right, take a look. We've got predictions. So you can see that we've got predictions over here, but this is currently making predictions off my desktop, which literally just says perfection is the enemy of progress. I'm actually going to drag this down. Let me just start recording. So right now it's making predictions based on my desktop, but this is where our candlestick patterns come in. Do we have it open? Let me just copy this. Copy. And open it up here. So now if I put this on the desktop, take a look. It's now making predictions of this region here. So it's making predictions of the last 8 candlesticks. So it's probably going to suck for the first couple. That's because I've trained it to make predictions of the last 8 over here. So we need to wait for those to populate. But you can see it's actually making predictions. So we've got evening star, morning star. So that's kind of sucky right now, but wait till we get the full 8. There we go. Bearish engulfing, bullish engulfing, doji, 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 bullish engulfing, doji, morning star, bearish engulfing. Have a look at that. It's actually running. All right, cool. So this is now running live. It's on your machine. You've also got the ability to do it off of images, but that is the basics up and running. So we're going to be able to train this from scratch on the data and you'll see how that all runs. Okay, so I'm going to stop recording now. What I'll also do is I'll switch screens so you can see what it looks like when it's running on my machine. Just give me a sec. I'll swap that over. Okay, so this is what it looks like when it's running on my machine. So you can see we've got bearish engulfing, doji, evening star sort of popping up, bearish engulfing. So you can see that this obviously is running with the dashboard on the other screen and the actual machine learning model or the deep learning model running on this screen at the moment. So we've now sort of covered getting it up and running, but what happens if you want to train it from scratch? All right, let's double back now and actually begin building the model. But before we do that, we need to get our data ready, right? So we're going to take a look at how we can transform raw images and labels into image patches. Okay, so I've talked a little bit about training from scratch, but why might you actually want to do that? Well, I've got a couple of key reasons, right? So let's say you wanted to change the model parameters. Let's say you wanted a bigger model or a smaller model. That's why you may want to train from scratch. You might want to train on different data. Let's say you've collected labeled data around different candlesticks. Maybe you've got different trading environments and you want to make predictions of something like MetaTrader or TradingView. You might want to train from scratch there. Also, if you wanted to change the candlestick patterns, you might want to train from scratch there as well. Okay, so now that we've got that out of the way and sort of setting the context as to why you might want to go and do this, let's go and start on our data model. Okay, so data is the crux of any good deep learning model, and that is no different here. So I've spent a ton of time on the data when it comes to this. And originally I had something like 10,000 images. I cut out a ton of them. I hand labeled some of them. Now, all of the data for this specific model and the model that you saw making predictions is actually here. This is all completely trained on this data. I haven't excluded anything. So I've got two data folders here. So I've got a train data folder, which is here, and a test data folder. Now you'll see that there's two different types. Let me make this bigger. So we've got hand labeled test and screen grabs. So this is, I've actually gone and generated synthetic data for the screen grabs, and the file to do that is inside of utils and inside of here. So it's data generation under screen. Let's make this a little bit smaller. So data generation underscore screen grab. If you want to take a look at how I wrote that, maybe go into it. If we want to deeper dive into it, let me know. But for now, we're going to focus on fine tuning using this data, or training from scratch using this data. So the generated images are inside of the screen grabs folder. I've also gone and used that dashboard, so the Plotly dashboard, and I've taken screenshots of that and hand labeled it. I've built, or I vibe coded an annotator. That's the only thing that I vibe coded here, because I didn't want to go and do this from scratch. And I actually went and annotated each one based on the different candlestick patterns. Now, when I was originally fine tuning this, I did have a nothing class. So I was sort of hoping that maybe I could have the model predict doji, bullish, bearish, morning star, evening star, and then a nothing class as sort of like a placeholder for everything else. It didn't really pan out. So I actually went and did some data modifications to sort of strip that out, and I'll show you that in a sec. But for now, just know that all of our data is here. I've also gone and split it into test and training data. There is zero overlap between the training data and the test data to prevent any data leakage issues. This means that when we go and evaluate our data on our evaluate our model on our test data, it's only going to be on test data. So we shouldn't get any overlap, and that should minimize the potential that we have like a variance problem where the model's been like overfit and it's just learnt a specific set of data. Now, inside of this folder, I've got labels.csv for each one of those. Really, really important, because this is what we use to load our data. If I scroll all the way up to the top, so there's basically a couple of columns. So I've got an index column. I've then got the name of the image here. So you can see that that's my image name. I've then got the class. So the classes are one, let's just jump into XColorDraw. So one is a doji. Two is, it's right behind my head. So two is a, bullish engulfing. Three is bearish engulfing. Four is a morning star. And five is an evening star. Beautiful, cool. Now, originally I did have that one class, or that zero class, sorry, which was gonna be zero, nothing. So if you see zero in there, it should be only in the hand labeled data. So if I scroll on down, so you can see that I've got zero classes here. I didn't end up using these for training. I ended up dropping them. So the classes, when they come out of the model, now sort of look like this. So in terms of labeling, they'll look like this, but from the actual predictions, you'll actually get, so this won't ever show up, so NA. So the doji will be 0, the bullish engulfing will be 1, bearish engulfing will be 2, this will be 3, and this will be 4. So that means I've sort of dropped, the nothing class, so it should look like this. So let me just add in a label. So labeled images, this will be model predictions. Cool, yeah, let's just add some backgrounds. Perfect, cool. I'll maybe include this screenshot inside of the GitHub repository as well, so you sort of have some background. Okay, so for now though, what we want to go on ahead and do is take a look at all the data stuff that we're doing. So inside of the repository, I've got a file. So if you go, so this is the root of the repository. If you go into source and into data.py, this is where I do all of the data magic. So there's a fair bit happening here, but let's take it step by step. So over here, we've got all of our dependencies. Then this is the core data class. So CLF data set. So it's just, I've called it that to stand for classification data set. Now, initially we've got all of the setup. So it'll actually go and look at the path that we've got the CSV and read it in. Then remember how I said I dropped the 0 class? So that's actually happening here. So I say, grab everything except for 0, and then I subtract 1 of the label to do that switching, right? So I go from 1, 2, 3, 4, 5 to 0, 1, 2, 3, 4. Cool, that happens there. And then I've actually got some data augmentation happening here. So basically this helps the model generalize, meaning it's going to perform better out there in the real world by having a couple of extra parameters thrown at it. The main one that I've got here is ColorJitter. So it adjusts brightness, contrast, saturation, and hue. And this should apply 40% of the time based on that parameter there, which is the probability that it gets applied. This is all done using a library called augmentations over there. Let me show you what that looks like. Augmentation. It's actually kind of cool. So it actually allows you to do, let me show you the ColorJitter one. So this is the parameter that I actually, fun fact, when I was testing this out, I didn't realize that hue was applied. So you can see right down here, I ended up disabling hue by setting it to 0. But this was switching candlestick colors from green to red, which meant it was extremely difficult for our model to work out what it was doing. So there, you just saw an example. It switched the color of the image from green to red. I'm pretty sure it was throwing it out quite a fair bit of the time. Whereas if I go and set it to 0 over here, so over here, I can disable the hue. And now take a look. It just adjusts brightness, contrast, and saturation. So that is what that step in the pipeline is doing. Now, I've also got a conditional argument here. So it's only going to apply if we're running it on a training data partition. So namely, we're going to run it on our training and our validation partitions. The rest is just a standard PyTorch pool. So basically, we define the length of our data set and we define how to actually go and get an item back. So we open up our image using Pillow. We then apply that augmentations transform, which is this over here. So we resize the image to 224 by 224. Some of this is legacy because I was building this originally based on Google's Vision Transformer architecture. So I've got a transform to convert it from 224 to 224. The original image is 700 by 500 pixels. I then crop it. Now this was fun, right? So I originally had it to pull 3 candles, because that's what the majority of the patterns look at. So it actually looks at the last couple of candles, and that's how I've gone and annotated. I then extended it to 8 candles. Honestly, I prefer it running on having a bit more data. But again, you can go and adjust this. If you do adjust these parameters though, that's gonna mean you need to adjust the model. So for now, just hold off. You can go and play around with it later on. These normalized parameters, these come from the ImageNet example that Google trained on for the Vision Transformer as well. So they basically normalize the image to this mean, or divided by this mean and by this standard deviation. Okay, so we apply our transforms there, we return our labels, and then we return our image tensor and our torch tensor. I'm talking a lot, but let me actually show you what this does. So over here, we create an instance. So this is, if you run this file, it's actually going to run through. So let me actually show you what that looks like. So let's get rid of our second terminal. So if I go and run uv run source, make this a little bit bigger, source data.py. This is going to create an instance of the data set and it's going to return one batch. So you can see here that we've actually returned an example. So we've returned back 32 images which have dimensions 104 pixels of height by 72 pixels of width, and they have 3 channels. Now, because I originally saved the image in PNG format, so let me actually show you the images. Just realized I haven't shown you the images. Let me go into desktop. Right, so I've got the data folders here. So if I open up train data and let's just look at screen grabs. So this is an example image. Boom, there's one. If I go and take a look at the next one. So you can see these are what all of our images look like, right? We've got all of these screenshots. So this is based on screen grabs, which means it's generated synthetic data. So this would be a bearish engulfing. This would be a morning star. This would be a doji. This would be an evening star. This is bullish engulfing, a bearish engulfing. These should be dojis, I think. We've got a whole bunch of different examples there. So when we actually go and run it, we're going to almost take a segment of it, and we're only going to bring back the last 8 candles. Now, you can actually see this for yourself by going and doing this. So if we jump into the data set, and what you can do is set this parameter, output samples, to true. Now, this is going to go into this images folder, and it's actually going to output an entire batch that's been transformed. So it's going to put it into the images folder, and inside of that, it's going to create another folder called transformed images, and it's going to loop through and generate a bunch of images. So they're just going to be numbered, and they're going to have scaled.png appended to it. Enough talking, let me actually show you that running, right? So if, again, you got to change output samples to true. Now, if I go and run this, we should get some images over here. Looks like no such file or directory. Oh, we've got to create it. So inside of images, I'm just going to create the file. So it's going to be transformed underscore images. Boom. Okay, let's run it again. Okay, so no errors this time. If I go and open it up, take a look. We've got our images there. So if we go and take a look at these images, so this is the cropped example. My head's blocking it. Let's move this over here. This is what our transformed images are going to look like. So this is what's going to be passed through to our machine learning model. There is going to be one additional transformation, and that is we're going to convert it into a set of image patches. I'll come back to this in a sec, but take a look. So it's captured, let me zoom in a little. So it's captured 1, 2, 3, 4, 5, 6, 7, 8. So we're actually passing through the last 8 candlesticks to our deep learning model to go and make predictions. So if you want to go and play around, you can actually go and, let's say we didn't want to run it on our test partition. So this is currently loading in our test data. What we could actually do is run it on train data as well. So if we go and change this to train data, it's going to pick up the folder. You need to point it to the folder where your labels are. So over here, so I've got labels.csv. So this should be fine. So I've gone and converted it from train to test. So let's go and run it. So if I go and hit clear, let's go and get rid of our images that we went and created. So if I go into images, transformed images, let's just delete all of these. So you can see that it generated 32 images as well. That's an entire batch. So if I go and clear this, let's go and run it again. So over here, transformed images. So we don't have anything in it right now. Remember, this is pointing at train now. So if I go and run it again, boom, we've got all of our images. So this is now run on a train sample. So play around with that. You'll see that it's able to go and take a sample from all of our data sets and actually go and run those generations. Okay, so that is what our model is going to get, but right, this is just the scale data, right? So we've gone and cropped it to only return back 8 images. How do we actually pass this through to a vision transformer? A key part of it is going in, converting it into those image patches. Because remember when we're playing around with LLMs, we generate an embedding, so that gives us a whole bunch of features around a particular token. How do we do this for images? Well, we convert it into a set of patches. So let me show you what this looks like. This is one of my favorite animations. So if we go into data.py, again, we can actually go and enable another parameter. So I'm just going to set output samples to false. You can run them simultaneously. It's fine. I'm just like, we don't need both. And I'm going to set output patches to true. So this is actually going to output patches and you'll be able to see them live on the screen. So let's go and run this. So if I go back and I'm going to clear this, we're going to run the exact same file. So uv run source data.py. This should pop up using matplotlib. Boom. Nope. Wait. Did it not work? Where are we? Oh, it's running on my other screen. Take a look. So that is our image patch. So if I go and close it now, please don't open up on this screen. It's going to open up on this screen. Boom. So that's what our image patches look like. So you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we've got 13 patches in height and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 patches in width. The cool thing is that, remember, patches is a hyperparameter. So we can actually choose, or it's a parameter. So we can actually choose how big we want our patches to be. So I've actually gone and set the patch size to be 8 by 8, which is the exact same patch size that we'll use in the model itself. Now you can actually see that based on the dimensions of each one of these images. So you can see that this is the pixel height versus the pixel width, which is, you can see, 8 by 8. But take a look. So it actually chunks up the entire image into a number of these little image patches. So this is actually how our model goes and makes those predictions. So we actually flatten these patches and send it through to our model. Over here, I've gone and converted them back into effectively height by width. But when we actually go and pass it through, let me actually show you this. We actually get a flattened example. So over here, this is an example. This is the rearrange function that actually converts or creates the patches. Now, if I went and printed this, so if I go over to here, print res, and let's just comment this out for now. And let's go and stop this script. So this is going to print out the output after we've gone and applied those image patches. So if I go and run source data.py, you should see that we don't have, what are we printing out now? We want res.shape, my bad. So this is actually printing out the examples. We don't need the examples actually printed out. Have we? I haven't saved it. Beautiful. Okay, take a look. So you can see that down here, we've got, so this is pre-transformation, right? So we've got 32 images, which have height of 104 by 72 and 3 channels. After applying the image patches, we have 32 images, which have 117 patches, and those patches are 192 values, which effectively represent the pixel values. So it's a flattened tensor. So we actually eventually go and convert it into a reconstructed image. Let me show you what that looks like, or the shape after I go and reconstruct it. So if I go and print reconstructed image dot shape, and this is just going to be a single image, right? Not all of the images. So we're not going to have the batch size. So if I clear this, take a look. So we've obviously gone and printed out all of them, but this is the example. So this is pre-transformation. So we've got 32 images, which have height 104 pixels by 72 pixels, 3 channels depth. Then we go and apply our patches, which converts it into 32 batches, because this is still a batched example. We have 117 patches in the sequence, and then we have each of those patches are 192 pixels deep. Then over here, we actually go and reconstruct it. So if I just pull out a calculator, right? So 8 by 8, 8 by 8 by 3 is 192. So you can see that there. That is where this 192 is shown there. Once we unpack that, we have 8 pixels by height, 8 pixels width, and 3 channels deep. So that is how the patches work, and that is our data. So we've chopped up our images and got them into patches. What next? Well, lads and lasses, it's time to build the ViT. We'll take the image patch function and embed it into the model, build out the full vision transformer architecture, and visualize each component. Let's do it. Okay, so we've now gone through our data model. Now it's on to the good bit, taking a look at the ViT itself. Now I've got all of the ViT stuff stored inside of a file called model.py. So inside of the root folder, you can go into source and then go into model.py. It is all there. There's quite a fair bit involved, but I'm gonna break this down step by step, and let's just collapse these for a second. The main class that you want to take a look at is this ViT over here. So this encapsulates everything that you need in order to have a vision transformer. And it's made or relies on these couple of classes over here as well. Our MLP block, our encoder block, our encoder, and our positional encoding. So I want to take you through step by step how this is actually built. But if you actually go back to the attention is all you need paper, what we're effectively replicating is this section over here. Now, rather, if you actually reference this paper, this is actually originally designed for translation, and this gets passed to a decoding layer. We don't go and do that for a ViT. We only use the encoding layer, and then this goes out into a classification head. So how exactly have we done this? Well, there's a couple of stages, right? Now, we've got our original image. We know that. We've seen it as we were taking a look at our data model. That image then gets converted into a number of patches. So remember, we chop it up and we can choose how big we want those patches to be. So originally, if we have our 104 pixels by 272 pixels, that gives us 22,464 pixels. We then go and chop it up into patches. And here I've actually chosen the patches to be 8 pixels by 8 pixels. That means that each patch represents 192 pixels of information. Now, if we go and chop up those 192 pixels, we've effectively got 22,464 pixels divided by 192 pixels. That gives us 117 patches. Now, let's go and take a look at how this plays into the model. So if you actually want to go and test this out, you can actually go to this stack component line that I've written down here, and you can visualize any one of these layers. So you can visualize the encoder block, the MLP block, the positional embedding, and the ViT. The ViT encapsulates the entire model, but you won't be able to see into some of these other blocks, which is why I've given you the option to do the others. So let's actually take a look at this. So if we want to take a look at the ViT, we just need to set this to -1. So it's going to pull the last one, and we can actually go and run this. So let's go and run uv run source model.py. We'll give it a second. Take a look. So this is our model in its entirety, right? Now, let me walk you through step by step. So this first layer here is actually what does the patch conversion. So it takes in a raw image and it converts it into its patches. So let me zoom out a little so we can see that. Takes in the raw image, converts it into patches. That gives us 117 patches of 192 pixels, right? Which is what I was sort of describing down here. So we're going to end up with 117 patches. Let me move my body by 192 pixels. Now, the thing is, when we actually pass it through to our ViT layer, we don't pass through the patch which has width and height. We actually go and flatten those patches so they actually look a little bit more like this. We've got 117 patches across the board, and they're 192 pixels. So we actually stack the red, green, and blue so that we have a flattened patch. That is effectively this layer over here. So we've actually embedded, so remember how we're taking a look at INOPS and how that went and created a patch? We've actually got this embedded over here. So if you actually wanted to go and change the patch size, you can actually do that here. The only thing is that when you want to go and change the patch size, the height and the width need to be equally divisible by the patch size. So I've actually got an assertion within the data file to show this over here. So you can see that I've got the height and the width. They need to be divisible by the patch size. Cool. All right. So we've taken a look at that. Let's jump back into our model. This then goes through a layer norm layer. We then pass it through to a linear layer. This is where we actually go and convert our flattened patches and pass it through effectively an embedding function. Similar to what you'd see inside of an LLM, we take our patch, we pass it through to embedding, we then get an additional number of trainable parameters. So we've now got 1024 pixels. Now, we still have 117 patches, but we've now gone and added trainable values that we can now use as part of training our model. So if we actually take a look, you've actually got trainable parameters over there. So 197,632. Again, it goes through another layer norm layer. And if we actually go and double back to our original attention is all you need paper, you can see that we've already computed the input embedding. What we then do is we then attach a positional encoding, which comes a little bit over here. I'll come back to this class token in a second, but we actually go and build that in and append it to our patch embedding. Now, before I go through that, well, let me actually show you that now. So if I go and run, let me actually show you this positional embedding. Now, the reason that we do this is that when we go and flatten our image and convert them into those image patches and pass them through to our self-attention layer or multi-head attention layer, which is the crux of a transformer, we don't actually have this concept of position embedded within that embedding. So position is actually really important, particularly for language model tasks, because position has meaning, right? Well, in our image, position has meaning because where the candlestick is going to derive which prediction we want to choose or which prediction is going to be the final output. So if we had a red candle after a green candle, well, that might be a bearish engulfing. Whereas if we had a green candle after a red candle, that might be bullish engulfing. This is why we want to have this position embedding layer to ensure that we encode position into the embedding itself. Now, this is actually done using a specific function. So if I actually scroll on up, inside of the positional encoding function, we've actually got this sinusoidal embedding function, which it comes from the original paper itself. So I think if I scroll on down, it is in here. I remember. Take a look. So this is actually the function for our positional encoding that we've actually taken directly out of the paper. We've brought this into our ViT, and within the ViT paper, it's included as well. So we can actually visualize what that looks like. So you can actually see sort of the drop off as you get further out within the sequence. So let me go and run this. So if we go right down, now we want to go and take a look at our positional embedding. So right now we're taking a look at our ViT. If we wanted to see the positional embedding, we can go 0, 1, 2, 3. So I'm just going to grab the third component inside of our stack components, which is going to run this code over here. So if we go and take a look, I'll leave our ViT because we're probably going to come back to that. Now this is going to render the image to the screen. It's just put on my other screen. So let me bring this back up. Take a look. We're actually encoding this concept of position and where we are within the sequence into our embedding. So this is actually the default function or a similar function that we use across a number of different transformer layers. But I thought that looks pretty cool and I wanted to show you nonetheless. Okay, so we've taken a look a little bit at our positional encoding. I can actually stop this now because it's running. Now, what we do though, and this is unique to ViTs when it comes to classification, is we actually append a class token to the sequence. So that's how we go from 117 patches to 118 patches. Now, I avoided answering this question before because you can see that we've actually gone from 117 to 118 here. That is because of that class token. Now, the reason that we do that is that right towards the end, we actually grab that class token back out after we've run it through the self-attention or the multi-head attention layer, which is over here. We grab it back out after we've gone and run it through our encoder block. Now, we do that because it's effectively a means of pooling the attention. Now, there's another way to do this that I've seen within some of the other papers where they just aggregate the output out of the attention outputs. I've used the class token. It works. You can play around with it if you want to go and adjust it. So we're able to do that as well. Okay, so now what have we also taken a look at? We've then got our encoder blocks. Again, this mimics what we've got inside of the attention is all you need paper. So if we actually go and take a look at this segment over here, right? And I go and show you our encoder block. So all of that is encapsulated within the encoder block. So if we scroll on up within the encoder block, that's all there. So if you take a look, we've got our layer norm. You can see that we've got our layer norm. So I'm just doing it prior to the self-attention. We've then got our self-attention, which is effectively our multi-head attention. So over here, we are passing through all of the same inputs, which is akin to performing self-attention. There is something unique here though. You can see these arrows and how they go from prior to the positional embedding and then get appended at the end. This is what's known as a skip function or a skip connection. So over here, I'm actually built that in. So you can see that I've got my X, which is our input. We then run it through our layer norm. We then pass it through self-attention. But take a look, right at the end, we add it back. That is our skip connection. And if you take a look further again, you can see there's another skip connection, which comes after we've actually gone and output out of the multi-head attention. We grab that and we add it back to the output from our multi-layer perceptron. So take a look. So Z1 goes through dropout. We then go through our layer norm into our multi-layer perceptron. So I've called it MLP here. It's the same as our feed-forward neural network. If I scroll on up, that is defined in our MLP block. So we've got a linear layer, we've got a GELU non-linearity. So this is just an activation function. We then pass through more dropout. We then pass it through another linear layer and more dropout. Now, if I scroll on down, where are we again? We're taking a look at our encoder block. So right down here, we then go and take Z1 and then we add it back. So that's our second skip connection. Now, if you take a look, there's an NX here. This basically means that we go and repeat this section multiple times. So we don't just typically have one encoder layer when it comes to building out a transformer. We'd actually stack multiple sequentially. And this is where the encoder comes in. We're able to tune how many of these layers we want. So if I wanted to have 10 or 20 or 12, I've got the ability to do that. Within this model, we're using 3. So again, I found that adding more of them tend to drop performance. Increasing the size of the embedding improved performance, increasing the size of the linear layers improved performance, but the more I stacked, the more training became unstable. I can actually show you this. So as I was training this, I kept like a massive log of what performance was looking like. So let me bring it up, I'll show you. So this is my Google Sheets log. So let me find an example. So right down here, when I increased, let me give you, I'll be able to pick it out. So this was, nope. Right, take a look. So this was only on was this on all data? 72, this would have been on all data. So when I increased the number of layers to 6, it was okay. When I increased it to 12, take a look at my test loss over here. So test loss sort of started out at 10.8 and then it ended at 0.882 at epoch, epoch 17. Now, if I went and increased the number of layers to 12, it really just got ultra unstable. So I went from test loss of 9.9 and I went all the way up to 5.75. This was with only a segment of data. So you can see that because I got 22 out of 22 batches. When I went and added all of the data back in, it was even more unstable. So I had train loss of 5.6 and originally at the start, and then towards epoch 10, it was 2.5. But you can see it was varying a ton when I came to test loss. So I found that also just to show you, this took a ton of time to work out how to get this right. So there was a ton of testing involved and it definitely went over a couple of weeks, but eventually I got it working. So a number of layers, I didn't find improved performance all that much. If anything, it made training a lot more unstable. There's probably ways that I could offset that, but I just found having a 3 number of layers tended to perform pretty well. Again, you can go and adjust this if you want to go and try it out yourself. So you can go and change the number of layers by adjusting this. So if I wanted to have 12 layers within my ViT, I've got the ability to go bump that up to 12, really easy. You can change that. Likewise, if I had more candlesticks that I had it within my data set, I can change that. So let's say I had 10 different candles, I can go and change that linear layer down the bottom there as well. Pretty cool, right? Okay, so that is what else haven't we covered? Okay, so we're back over here. So we've taken a look at grabbing our attention output. So we've taken a look at applying our embedding, inserting the class token, adding in the positional encoding to give the concept of position. We then run it through our encoder block. So again, if we take a look at our model, we've got 3 encoder blocks, 1, 2, and 3, which then go to our linear layer down the bottom. So we've got all of our positional encodings. We then run it through our multi-head attention layer. We grab our first token because that's what we want our model to attend to. And then that then gets passed through to a classification layer. And this is inside of the ViT. So right over here, you can see that I've got my final classification layer, which is a linear layer over there. So it takes in 1024 values and outputs 5. Those 5 should be our final predictions. They should be a doji, bullish engulfing, bearish engulfing, morning star, or evening star. So the model is all built out. How do we kick off training? Well, we'll partition the data sets to get clear performance metrics, and there's one last data augmentation I want to talk to you about, which happens at the batch level. Onto training we go. So we've gone through our data component, we've gone through the ViT model itself. It's time to get training. So there's one key thing that I wanted to show you in training. It's just one last augmentation that I went and applied. This helped get the model performing pretty well. But it was a nightmare to begin with because it was just throwing everything off. But I'll show it to you regardless. So we are bringing in our model. We're also bringing in our classification data set. We're bringing Torch, a bunch of other stuff. We're also bringing the data loader because remember, we're going to batch. We are also bringing V2, which is effectively augmentations, but I think it's embedded inside a Torch Vision. And Torch Info Summary, you've already seen that already. We used it a bunch inside of the model. So remember right down here, we're actually using the Torch Info.summary to output those different model structures that I was sort of showing you. Okay, but for now, let's actually take a look at our pipeline. So first up, I set the manual seed to 42. So this ensures that we have repeatable random start points for our training and testing data set because we do have shuffle set. Now over here, remember when we built up our data set, we actually passed through the path to our labels? Well, that comes through here. So you can see that we've got our path to our train labels inside of data /train data. So remember, if we go into data and train data, that's our labels.csv file there. We're just passing it over here to our train data set. Now remember, in our data model, we also had the ability to disable and enable certain transformations inside of augmentations. We could set it to train or false, or train equal to true or false over here, which would disable or re-enable color jitter. Well, over here, I'm setting train equal to true, but just for our training and validation partitions. Then I've also got my test data set. So this is going to be that separate partition. So it was, remember, I've got train here. I'm actually going to split train into training and validation. So that way we can use validation to train hyperparameters. Plus, I think I had some data leakage between the train and original validation partition. So I just combined them and then set up a random split, which you can see right over here. Let me close up. Perfect. So we've now got our training size and I've set that to 70%. And then I've set up our validation partition to be the rest of it. So keep in mind, it's good practice to have training, validation, and testing. I didn't originally when I was building this and it just caused everything to go haywire. So just good practice, make sure you do it up front. Okay, this is the bit that I really wanted to focus on. So this is the last augmentation that I applied. So it's called cut mix and mix up. So they're two different augmentations, but let me just show you what they do. So cut mix versus mix up. So this is a really good animation or visualization of what it does. So this would be like a raw image. This is what mix-up does. You can see it blends an image of a dog and a cat together. And this ensures or helps our model generalize on images that it may not have seen before. Cut mix actually takes chunks out of different images and blends them together. This is why you need to apply it once you've actually batched up your data so that you've got an entire batch to mix up and to cut mix. So this is why I've applied it over here. But let me actually show you the impact on the labels because I should probably show you the image as well, but I haven't planned for that. So maybe I'll do that in another video. You guys let me know. I was also thinking maybe we'll do another one on how to add in new candlestick patterns as well. If you'd like that, let me know in the comments below. Okay, but for now, let me just show you the impact on the label. So I'm going to go iter on our train data set. So we're going to iterate through that and I'm going to grab the first batch, which is going to return a sample, set that equal to true, and then we're going to get back X and Y from our sample. So it's going to return a tuple and then I'm going to print out Y. So this should print out our labels. Now let me show it to you with cut mix and mix up disabled. So I'm just going to comment that out over there. So it's actually embedded within the collate function and I've got this ability to apply a random choice. So this determines whether or not we apply cut mix, A, mix up, B, or whether or not I apply nothing, which is this identity function over here. And I've actually set up a bit of a probability distribution here. So basically probability, what is a mass function. So we've got the ability to go and apply cut mix 25, or it's going to apply cut mix 25% of the time, ideally mix up 25% of the time, and the identity function, aka no transformation, 50% of the time. Okay, so if I print out Y, you should see a couple of different examples, right? So I'm just going to clear this and I'm going to run uv run source train.py and take a look. So keep in mind, this is with it disabled. So this is what our labels look like. We've got really distinct classifications. We've got 1, we've got 2, we've got 1, 4. So remember, we've got 0, which will be a doji, 2, which will be what? Bearish engulfing, 4 will be an evening star, 3 will be a morning star, evening star, so on and so forth, right? So they're really distinct labels. Now watch what happens once we apply cut, mix, and mix up. So this is going to blend not only the images, but also the labels together. So if I go and run this again, take a look, dramatically different. So you can see that they're now blending label 0 and 1 together. So this is going, when you actually take a look at the image, it's going to be a blend of a doji and a bullish engulfing. This one's going to be a blend of a bullish engulfing and a bearish engulfing. But you can see it begins, not only blends the images, but also blends the labels. This ensures that our model doesn't overfit, and it also improves the performance in terms of generalization. Now, because I have also passed through the identity function, you're going to get some labels which aren't adjusted at all. So you can see that there. So we've got a clear, what is that? 0, 1, 2. So that'll be a clear bearish engulfing, which shouldn't have any transformation applied. Now, I found that adjusting this parameter, like going way too much on the cut mix up, it tended to throw the model out. So, and it sort of limited training. Adding it back in definitely improve performance in the long run. You might choose to change that if you want to go and fine tune. But again, you're training it, so you've got the ability to do whatever you want. If you want to go and play around, let me know how you go. I'll be super interested to hear how your performance runs. Okay, so but let's quickly bang through the rest of this. So we've got our validation partition, which we've sort of prepared up there. That's not going to have cut mix up applied because we ideally want that to mimic what it might be like in the real world. And then we've got test data, which is completely out there in the real world. We then create an instance of our model. I'm then printing out the summary so you can see what the output looks like. And remember, our image is going to be 104 pixels high by 72 pixels wide. Then we can tune the number of epochs. So if you wanted to train for longer or less, or more or less, so let's say I wanted to train for 50 epochs, I could choose to go to 50 or 100. I could go to 400. When I was first starting out, I actually had 400 as my default and just banged it out. Didn't really perform that well. I actually found like best performance after around about 25 epochs. So, I mean, play around with it, see how you perform. But you're actually going to see the performance when we actually kick off training. I've got an animation towards the end. We then set up our loss function. We're going to use cross entropy loss. This automatically applies a softmax function, which gives us a probability output. Then I'm going to set up my optimizer, which is going to be the atom optimizer. We pass through our model parameters, and I've set the learning rate to 1E4, which should be 0.0001. I've actually written it up there. If you wanted to slow down the learning rate or speed up the learning rate, you've definitely got the ability to do that. So let's say I wanted it to be 0.001. I could actually just drop the exponent, which is going to be -3. Beautiful. So that is our learning rate. I've also set up a learning rate scheduler. So basically this means that we're going to slow the learning rate over time. And this is the cosine annealing warm restart. So basically after 30 epochs, it's going to restart the learning rate at a higher rate. And every time it restarts, it's going to increase the length of that restart. So it's going to slow down. This basically means that we don't find a we find a local minima rather than or it prevents us finding a local minima rather than a global minimum. So, and effectively improves performance overall in a nutshell. So this multiplier basically says that after a restart, it increases every time we reset that learning rate higher. So again, you can play around with that if you want to change it. Okay, so what else do we have? Then we basically start our standard training loop. So we set our model to train. We then go and accumulate epoch loss. So for each batch, we're going to extract the sample, so effectively the image and the labels. We then pass it through to our model. So we make a prediction. We then send that through to our loss function. We calculate our loss. We zero out our gradients. We compute the gradients. We then apply them to our model via backpropagation. And then we take a step on our scheduler. So again, that's going to slow down the learning rate. And then I've built a fancy progress bar. That's the explanation. Then we do the exact same thing, but we do it for our testing partition and our validation partition. Validation partition first, you can see that over there. And we set our model to eval. So this should disable all of the dropout throughout the model as well. So we do it on our validation partition, we then do it on our test partition, and then I've set this up down here so that it saves the model every 5 epochs, and it's going to save it into the checkpoints folder. Okay, let's kick off training. So that's our training set. So if I go and run UV, so everything's uncommented, right? Yeah, we're looking good. So if we go and run UV, let's also double check we've got a checkpoints folder. We do. So right now I've got 25 models. So let's bring this over there so we can see it. So we can go UV run source train.py. Take a look. We are now training. So right down the bottom, you can see our training. We've also printed out the model summary. This is still printing out the labels with cut mix up applied. But take a look. Right down here, we're training. So we're on epoch 1 out of 100. And this is running on my MacBook right now. It's running reasonably quick. Let's give one batch a run and then I will hide myself and we'll let it run and we'll come back for testing. Okay, so you can see our performance there. So we can see, let me move my body. So we've got, how do I do this? All right, I'm just gonna hide myself. So you can see that we've got our training loss over here, which is 1.8031. We've got our validation loss, which is much lower, so 0.2497. And we've got our test loss, which is 0.917 over there. I'm just gonna minimize this a little bit so that way it looks a little bit nicer. But basically, ideally, you should see your train loss, your validation loss, and your test loss decrease over time. So I'm gonna let this run and we'll see what performance looks like once we've gone through. Let's wait for maybe like 25 epochs and we'll see how we go. So roughly, if you sort of wait till then, performs pretty well. All right, cool. I'll see you in 25. Alrighty, and we are back. So we've gone and trained for what it feels like 25, 26 epochs. I'm gonna stop this now. And if we go and take a look, looks like we've performed pretty well. And keep in mind that the loss on here was a little bit unstable, but it actually, we'll test this out and see how it performs on some actual data. Now, if we go and take a look, you can see that under checkpoints, we've now got checkpoints 0 through to 25. And if we take a look at our losses, I'm just gonna hide myself again, so it's a little bit easier to see. So we can see that our training loss has definitely decreased. So we started out 1.8031 and ended at 0.5168. The only thing is that we did reach, it might have be an indication that we did start overfitting, because if you take a look over here, we had really low value validation loss. We also had really low test loss, and this came at around epoch 13. So the closest to that will probably be around about epoch 15. So we could also use epoch 10 as well, because that was performing pretty well around there. Now, what we actually want to go on ahead and do is test some of these out. So how do we go about doing this? Well, and also keep in mind that your training metrics probably going to be different to mine. So again, you're going to start at different endpoints. Your model's going to converge at a different rate. So if we actually go and take a look, let's go and see how we can load up some of these checkpoints. Inside of the source folder, I've also got a file called test.py. We can actually use this to go and test out our predictions. So over here, we can choose what data set we're going to use. So we can use our test data. You can see that that's loaded over there. And this should return a grid, and it's going to return a new file called results.png. So we can actually test this out and see the performance. Now over here, you can choose which model you want to go and use. So under line 23, we're going to use the torch load.static function, and this is going to load in our weight. So let's say we wanted to load checkpoint 0, checkpoint 5, we've got the ability to do that. So let's try checkpoint 0 to begin with. So if I pass through 0 there, and what I'm going to do is I'm just going to clear this. And if we go and run UV run source underscore test or /test, we should get a results file over here. So that's all printed out. Let's take a look at our results. It's actually performing pretty well, even though we haven't trained for that long. So take a look. So actual, and so this is the actual prediction, this is the actual value, which is bullish engulfing. It predicted bullish engulfing. Actual bullish engulfing, predicted bullish engulfing. Actual predicted bearish engulfing, predicted bearish engulfing. Morningstar, Morningstar, bullish, bullish, doji, doji, bearish, 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 bearish. So even though we've trained for barely any time, it's actually performing really well. Keep in mind, it took a long time to get to this point. So, or to get the model performing this well. So we can also go and test a beefier model, or one that's been trained for longer. What if we tested around 10? So let's go and use 10. Actually, let's test one more sample on 0 first. So I'll just keep results up. So you can just run this again. So if I just go and run, let me clear this so you can see it. All right, so if we go and just run, let me move my head out of the way. So if I go, let me just hide myself. Actually, it's probably easier. So if we go and run UV run, what is it again? Source underscore test. So this should bring back a different sample. Okay, so how do we do this time? So bearish, 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 Morningstar, Morningstar, bullish, bullish, doji, doji. Not too bad. If we go and test again, so we haven't got one wrong yet. Interesting. Pretty good considering that was at the 0 point. So if we go and test, let's test around 10. So 10 seemed to perform pretty well based on our loss metrics. So I'm just going to change the model to 10 underscore model over here. And if we go and run test again, let's jump back to results. How'd we go? All right, so we got one failure, a couple failures. All right, good. It's always a good sign. It's always worrying when it performs perfectly. All right, so we've got actual Morningstar, Morningstar, actual bearish, bearish, actual bullish, bullish, actual doji, doji. So here, the actual was Morningstar and it predicted doji. Okay, so that's one failure. This one looks like I might have had a data issue. So you can see there, that typically happens when the Plotly dashboard disconnects and then you get this error sort of popping up. Okay, so we had a couple of failures there. What if we ran it again? Okay, so bullish, bullish, bearish, bearish, Morningstar, 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 evening, evening, doji, doji. So still pretty good. So this one actually got the doji. I don't know. It looks like the errors predicted the errors were dojis. Who knows? All right, let's test out our final model because 25 was the last one that we had. So if we go and run this, but they're all performing pretty well so far. So if we go back to our results, let's test it. So I'm just going to run UV run source test. The only thing I changed was the model that we're using. So let's go back to our results image, which again is just going to output into the repository. Okay, so we had another set of predictions. So bullish, bullish. Let's make this a bit bigger. Bullish, 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 evening, evening. Bearish, bearish, Morningstar, Morningstar, bullish, bullish, doji, pretty good. Test again. Take a look. Doesn't look like we had any misclassifications there. Let's do it another time. Pretty good again. One last time. And pretty spot on. Alrighty, that is our model now trained. So we've successfully gone and trained it for 25 epochs and we've tested it out on our test partition. So that's our model trained. Final stage, real-time predictions. I'm going to walk you through the real-time prediction capability. This is where the model really shines. When I originally tested this with GPT-4, it was way too slow to make predictions in real time. The code is here if you did want to test it out though. Onto real time. So we're in the final stage, just making real-time predictions. Now we've kind of already done this already, like right at the start with the pre-trained weights, but I'm going to show you how to load the weights that you've just gone and trained yourself. So the first thing that we need to do is start up our dashboard because this is how OpenCV is going to get predictions. Now, if we actually jump into candlestick prediction, there is one thing that I want to point out. So when you actually go and make a prediction, it's pulling the screenshot from your monitor. Now, I've customized this based on running on a 4K screen. You might need to play around with the image size if you're running on a different size screen. If you do have problems with this, let me know and maybe I'll just chuck in the code inside of the GitHub repo. But for now, we're gonna run it and I've also got the camera over here so I can sort of show you what it looks like on both screens because OpenCV is going to grab a screenshot from my monitors over here. I'm then going to load it and I will crop it as well by passing it through to augmentations. You can see that I'm resizing it back to 224. Before that, resizing to 700 by 500. And this crop is actually just taking the top screen because by default, when I use, I think it's MSS to capture the screen. So over here, what is actually going to happen is it's going to capture both screens. I only need the top one, which is where I've got the dashboard running. Okay, so what we're going to do is we are going to go on ahead and make some predictions. Now, keep in mind, inside of here, we can choose what checkpoints we're going to load. So right now it's loading 25. Let's say we wanted to load, I don't know, 15, for example. I could chuck that in and it's going to pick up from this folder over here where we've got our trained weights. But for now, what we're going to do is we're going to start up the candlestick dashboard. I'm going to switch the screen that I'm recording in so you can see the final predictions, and then we're going to kick this off. Okay, so let's start up this dashboard first. So I'm just going to clear this. Actually, what I'm also going to do is let's change the candle. So let's say we wanted to do it on Apple. You could go and change the different stocks. This is just using Yahoo Finance right over here. You can also change the period, the interval as well that you want to make predictions. So that's that done. I also want to slow it down a little bit so that way you can see the prediction. So this means that we're going to get a new candle. Let's maybe do it like every 3 seconds. So that means we're going to get a new candle every 3 seconds. All right, let's start this. So if I go and run UV run source utils candlesticks, that should start up our dashboard. Boom, we can hit that. Give it a second. All right, cool. So we've got candlesticks populating. We now want to go and start our predictions, but keep in mind this is going to populate on another screen. So I'm just going to switch the screen that I'm recording OBS on so that way we can see it on the other screen. So give me a sec. Okay, so I'm just going to start the camera as well. Okay, so I've now got the candlesticks running up on this screen. And what we're gonna do is we're gonna start the predictions and get that running ideally on this screen down here. So let's start this. So I'm just going to create a new terminal. We can go UV run candlestick prediction.py. So let's see how we go. We wanna have the candlesticks on this screen and then the predictions on this screen. So let me move my head out of the way because I realized I was in the way the majority of the time. Let me hide myself. Beautiful. All right, let's go. All right, so there we go. We've got an evening star populating, another evening star. So you can see that there. We've got bullish engulfing. And again, you can see the probability here. We've got a big bearish engulfing. We've got a doji. We've got a morning star. How good is that? Morning star, so sort of continuing the pattern. I've noticed that with the morning star. We've then got a doji, evening star. So that's one other thing I noticed, like when it doesn't have, sometimes the bullish engulfing doesn't fully encapsulate the red. Again, we could add more data, but take a look. We've got bearish engulfing, bullish engulfing. You could also filter these out, right? So drop the lower confidence probabilities and just bring back the really confident ones. Got our morning star, doji. That's probably not the greatest doji, but again, it's low confidence. We've got an evening star. That's a really good evening star. We've got a doji. And take a look, that is our predictions happening in real time. And again, if you wanted to speed this up, you could do this as well. So I just need to jump over back into the code and I sort of showed you where I sped it up, right? So if I pause the predictions and pause the dashboard, so you can see I'm stopping both. And then if we jump back into our candlestick code, let me bring it onto this screen. If we jump back into our candlestick code, we can just drop this number. So if we wanted to go fast, we can set that to 1. You could even go even faster. I'm going to put it back onto the other screen. Let's make some predictions. Start up our dashboard. Start up more. Actually, let's do another stock. Let's what's a popular stock? Let's do Broadcom. So what's the stock code for Broadcom? Actually, let's do Nvidia. That might be sick. Okay. So I'm going to stop. Let's bring the code down. So again, all you need to do to change the stock code is change the candle here. So I'm going to set it to NVDA. Going to restart our dashboard. So clear that. And then we can start up our dashboard again. It should pick up NVIDIA and it should be faster as well. So if I go and run that, and then I'm going to run the predictions. I'm going to move this back onto this screen. Okay, so we've got our candles over here. Let's bring our predictions down. Okay, so you can see that running. So we've got the dashboard up here and then we've got live predictions. So take a look. And again, remember, this is going to use 8 candles. So until you get 8 candles, it probably won't predict all that great, but once you get 8 candles, should be good. Take a look, doji. Alrighty guys, and that is how to build your very own candlestick detection model. Hopefully you've enjoyed this tutorial. Let me know in the comments below if you get stuck. I'm going to be updating the code. Again, just ping me. Thanks so much for tuning in guys. Catch you in the next one. Peace.